All right, we're on to chapter 11 with gases. So start off with converting between units. So pressure is 125 psi, that's pounds per square inch. What is this in millimeters of mercury? Also note something when you measure like a bicycle tire or an air tire, like on your car, the total pressure is actually the atmospheric pressure plus that. Like when you have a gauge, I should say. So sometimes you say PSIG, that's PSI gauge, or PSIA, that's the absolute, that includes the ambient pressure. So this would be PSIA, indicating the ambient pressure. So just so you know, if you're checking the pressure, like I said, in like the tires of your car, it's actually the ambient pressure plus whatever the pressure of what's in the tire. So let's convert this to millimeters of mercury, and you just use the conversion. I like this. I keep the numbers memorized per atmosphere, and here is the chart here. And so 125 psi is 14.7 psi, multiplied through 760 millimeters of mercury to get 646. Well, actually, sorry, it's 6,460 millimeters of mercury. So another thing, though, that's a quick conversion if you're ever wondering about pressures per feet. So 33 feet of water is going to be 15 psi. It's about 50. It's 14.8. I'm sorry, 14.7, but it's like 33 feet or 10 meters of water. So if you're wondering how to quickly do calculations to see what the pressure of water is going to be from water towers, or how much pressure you need to pump water uphill, or if you're a firefighter, that's kind of what they teach you, is 100 feet for 15 psi. So, or 10 meters, I guess, if you're in Europe or something, kind of thing. So Boyle's law. This is we're going to go through a couple of different laws, building up to the ideal gas law. Personally, I just deal with the ideal gas law, but we can do these individually. One equation, one unknown. We know one pressure, one volume, and the other pressure, we need to know the second volume. So apply Boyle's law and solve for it, and the volume is 24 liters. So it's just the plain old one variable, or one unknown, one equation. So solve for that, and something called degrees of freedom. You have, for the number of variables that you have to have that many number of independent equations to solve for that variable. So that's one of the fundamental theorems of, not the fundamental theorem, but one of the fundamental foundations of mathematics when it comes to these things. So keep that in mind when you're solving for unknowns, and you have to have a single equation per each unknown. And this is just a one-to-one for this one. So let's do Charles' law. So with this again, we're going to be given temperature and volume. Two are known, one is unknown, and also asking for the temperature, degrees Celsius and Kelvin. So when you apply Charles' law, you have to use Kelvin temperature. So we're given two volumes and one temperature, and we have to find the second temperature. So you use Charles' law and do the just look for one of the unknown variables. So you solve for the variable, and there you have it. The unknown temperature is volume 1 over volume 2 times the second temperature, and you have to convert that to Kelvin. And so the second temperature is 297 Kelvin. And then you subtract the 273 for the Kelvin to get 24 degrees Celsius. So you have two answers there potentially: 273 Kelvin or 24 degrees Kelvin, whatever, or Celsius. I'm sorry, 24 degrees Celsius, whatever one it's looking for, or whatever one you are looking for. So look at the combined gas law. So we're not quite at the ideal gas law, but we have more terms. So let's see, we have an initial volume and a pressure and a temperature, and if we're going to compress it to a new volume and a new temperature, what's the final pressure? Okay, so we still have one equation and one known, one unknown. So this is assuming the same number of moles of gas. So the amount of gas is not changing. So and we're just looking for the second pressure. So we do the combined gas law, and then we pick our unknown. So our known is going to be P2. We can do P1. It just doesn't matter. It doesn't matter. Just as long as you're consistent with this. You need to be consistent as far as where you assign the pressures, volumes, and temperatures for each. So doing that and making sure the temperatures are in Kelvin, that's another common mistake, is not doing absolute temperature. And then you get the pressure there of the so 1.25 millimeters of mercury. So single equation, single unknown. So Avogadro's law. I always think about blowing up balloons with this one. Put more moles of gas, the balloon gets bigger. So 4 liter sample contains 0.22 moles of helium. How many additional moles of helium do you need to obtain 6.4 liters? So this is just like the other ones where you have it's a direct proportional, not inverse like Boyle's law. It's a direct proportion, and one equation, one unknown. So we do this, and the second number of moles is 0.29 moles. So, but we can't stop there, because it says how many moles do you need to add. So you need to subtract the initial. So the change is always final minus initial. So final minus 0.29 minus 0.22, and we get 0.07 moles. So that's the number of moles of gas you need to add to get the new volume. So moving on to the ideal gas law, and this is the ideal gas law is the one that I tend to work with, and at least the start off, it's pretty easy to memorize. All right, PV equals nRT. So if you don't memorize it, you can always write it down and keep it somewhere safe and close to your heart, like everything in this chemistry class, of course. So what's the volume occupied by 0.875? It doesn't matter the type of gas. Ideal gases all act the same. At a pressure of 1.37 atmospheres and temperature of 315 Kelvin. So find volume. So PV equals nRT. Solve for volume. V equals nRT over P. And then put in the numbers. R is a gas law constant. It doesn't change. It's actually Avogadro's number times the Boltzmann constant. If you're wondering, the units are 0.08206. I know it a little further than the book. Liter atmosphere over mole Kelvin. So you notice that all the units cancel, and then you're left with 16 liters at the end. So putting the numbers, and also make sure you put the numbers in your calculator correctly. So that's another skill. That's another problem that some students have, is not putting the right numbers in the calculator. So ideal gas requiring unit conversion. So similar, but we're going to have to change the units, and here specifically is the pressure. So we have total pressure of 24.2 psi and a volume of 3.2 liters, 25 degrees Celsius. How many moles of gas do we have? So we find the number of moles of gas, and same idea. So it's going to solve for N. N is the number of moles of gas, so N equals PV over RT. But now we have we need to figure out the number of we need to figure out the pressure in atmospheres. So we're going to convert psi to pressure in atmospheres, and then put the temperature in Kelvin, and then put the units in. So there's a couple ways you can do this. There are certain R's. You can look up R's for different units. I don't really like doing that. I like just converting everything to atmosphere. That's the way I do it personally. So, but it's whatever floats your boat. If you want to memorize or look up the different values of R, that's a certainly a valid way to do it. I like the way the book does it, where we just do everything in atmospheres. So let's do molar mass, ideal law, and mass measurement. So another one. So with ideal gases, sample gas has a mass of 0.311 grams, volume is 0.225 liters, a temperature of 55 Celsius, pressure of 886 millimeters of mercury. What's its molar mass? So molar mass is moles per liter. Grams per mole. So like water is 18 grams per mole, for instance. So we're going to take the 0.311 and divide it by the number of moles of gas, and then put that in our calculator, and then it'll tell us the molecular mass. So we have the terms there, and we need to solve for the number of moles. So solve for the number of moles, right? So mass over moles is the molecular weight. And so we're going to solve for n. And we solve for n as before, the PV equals nRT, and make sure we have the right units in both pressure and temperature. And then we get 9.74 millimoles. So, or 9.74 times 10 to the minus 3 moles. So then we take the mass divided by the moles and we get 32 grams per mole. So doing it there like that probably is oxygen then, right? Because that's 16 times 2. So total pressure and partial pressure. So when you deal with ideal gases, they don't interact, so you can just throw different gases in there and the pressures just add. Mixture of helium, neon, argon has a total pressure of 558 millimeters of mercury. Partial pressure of helium is 341, and the partial pressure of neon is 112. What is the partial pressure of argon? So the total pressure is the pressure of the helium, neon plus argon. And we have, then from that, we have one equation and one unknown. So we're just going to solve for the pressure of argon. It's going to be the pressure total minus pressure of the helium minus pressure of neon, and doing all that, we get 105 millimeters of mercury, just plugging in the number. So this is an easy one. You just have to remember the relationship, right? And it has to deal with Dalton's law of partial pressure. And partial pressure and percent composition. So this is important for scuba divers. So you want a heliox mixture that, what's the partial pressure of oxygen that breathes a heliox mixture containing 2% oxygen at a depth of 90 meters with a total pressure is 10 atmospheres. It's pretty far down. So how do we do this? So you just multiply it really, the 0.2% times 10 atmospheres, and it's a straight shot multiply. So it's going to be 0.20 atmospheres, which is the same as at sea level. So the scuba diver, or I should say diver, well, I don't know what suit the person is wearing, but this is going to be relatively comfortable for the diver, I suppose, down here. It would scare me, but that's why I'm a teacher and not a diver, I suppose. Gases in a chemical reaction. So now we're going to combine the concepts of stoichiometry, which you can't forget anything in this class. Remember that with chemistry, you cannot just stop and then I will never use this stuff ever again and I'm going to forget it. No. You cannot do that because everything builds up upon it. How many liters of oxygen gas form when 294 grams of potassium chlorate react in this reaction? So 2 potassium chlorates form 2 potassium chlorides and 3 moles of oxygen. So assume the oxygen glass collected is that pressure and that temperature. So what we can do here, so once the liters, from the equation we can figure out the number of moles of gas, and then we have pressure and temperature and number of moles of gas, and using an ideal gas law we can get the volume. So that's the idea from that. At least this is how you solve it. So now we got to start off with getting the number of moles of gas. So let's do doing the molecular weight, what you've done before, and then do the molar ratios. So 294 grams of potassium chlorate, so convert to moles, and then do the balanced chemical equation with the moles of oxygen. Now we're left with moles of oxygen. So ideal gas law, P equals nRT, solve for the volume, include the numbers then for the pressure to change it to a little under an atmosphere, and then solve for the volume, and again making sure that the temperatures in Kelvin is 90.7 liters. So multiple step problem. Some students may have a hard time combining these steps together, but this is all things you've learned how to do. So of course, understanding each individual step, that of course helping you as my job. Your job is to integrate this knowledge. So you, as a student, you need to be able to see these and then to be able to combine the ideas. And I mean, learning happens in your own brain though. So for me, I like to communicate to you, think of moles to keep on, that's like the center of it. the moles of material. And when you approach these problem, like where are the moles going, kind of thing, and you're because I kind of for me as a chemist, I get a mass of something like, well, what's the moles? I need to have units of molecules and atoms. So try and keep that approach, where you're approaching things in terms of where the atoms and molecules are and where they're going and how they're reacting. And then, oh, it's a gas. Like, all right, so if it's a gas, what am I looking? I look for a volume, and okay, I look for the volume, and now I'm given the moles of the mass of the reactant. I can turn into moles of reactant. I can turn to moles of product. Now that I know the moles of product, I have the numbers that I need to solve for the volume using the ideal gas law. So you as a student, like I said, you need to be able to integrate all this and be able to strategize and put it together. So this is a more difficult problem, like I said. So I mean, look it over, think about it if you're having a hard time, and then sleep on it, and hopefully, and sleeping does help. In your dreams, you do. Sort out material in your mind, and I've had lots of strange dreams when it comes to things I've studied, so that's a good sign. Shows you're learning, and so think of moles of gas when you're sleeping tonight, please. So let's use molar volume in calculations. I tend not to do this, to be honest with you. I tend to use ideal gas law, but sure, because standard temperature pressure, it's only under very specific circumstances that you can do this. It's not a very commonly used thing. It's infrequent when things are at standard temperature and pressure. But and it's also weird because for gases, for everything else, standard temperature and pressure is 1 atmosphere and 25 degrees Celsius. So I don't know why for our moles of gas we decided to use 0 Celsius, but that's fine. So how many grams of water form when 1.24 liters of hydrogen gas that at standard temperature and pressure react with oxygen? So we can use the 22.4 liters of hydrogen for this, and remember, this is at 0 degrees Celsius. It's not the 25 degrees Celsius that we use for the other standard states. We're weird. Why would we have uniform standard states, right? That would be too easy on you students, right? Why would we do that? Because we are lazy and dumb and we're stubborn. So different standard states, 0 degrees Celsius. And so from this and using the balanced equation, the nice thing is it's a 1-to-1 or 2-to-2, or you're going to say 1-to-1 molar ratio between water and hydrogen. So we convert then to so we start with liters of hydrogen, convert to moles of hydrogen, convert to moles of water, multiply by the molecular weight of water, and we get just about a gram of water. So that makes sense. So thank you for listening, and I hope you enjoyed the homework discussion, and I hope you have some wonderful chemistry dreams tonight. So goodbye.